recording first, I guess. Again, good morning. I just was basically talking before the recording started, and the fact that these classes are recorded. For those who cannot make it, they make sure that they basically watch the recording, because there is assignment that is graded for this class, unless you guys decide to skip the participation, which is going to hurt your overall grade. Anyway, so again, we are still talking about waves. There is something, let me share the screen in here quickly of what we did so far. Yeah. So this is chapter 15. We're talking about basically the fact that we have these waves. And last time we spoke with, before we actually promised to do some problems in here, is about standing waves. What we saw then is that basically, if I have the string of a fixed length L, and it's fixed from both ends, then in this case, I can have different modes actually are called. In this case, in which case I can have one NT node and two nodes, because those are the points where the string is fixed. And that is basically the combination in this case of the incoming wave being excited on one side and the reflected wave on the other side, and they combine to give me this beautiful structure. The mathematics actually was done leading to this one. This is the expression of the combined wave. So the condition that the fact that both ends are fixed, meaning that y is equal to 0 regardless of what the time is. Obviously, this is true for x equals to 0 if we take one end to be the origin of the wave, and the other end basically being L, that needs to be also fixed, namely sine of KL equals to 0. Well, sine of KL equals to 0 has many ways of writing that expression. Namely, k times L can be pi, or can be 2 pi, or can be 3 pi, or can be any integer numbers of pi's. And that is actually the essence of this modes, because the product of k times L is an integer times pi, where n can be any number from 1 to, it cannot be 0, because then at the end I will have basically no wave at that point. Anyway, the point being in here is that n is equal to 1 is a mode, n equals to 2 is another mode, and so on and so forth. And this is basically how we look at them. We can visualize them in terms of the wavelength. So the wavelength can be in such a way, first of all, when n equals to 1, that means lambda is equal to 2L. That means the wavelength is twice the length of the string. That means what I'm looking at in here is half a wavelength, okay? So this is a so-called fundamental mode, okay? And then n equals to 2 is another mode, and this is an overtone. Actually, this is the first overtone in this case. This is the second mode, and that is n equals to 2. Obviously, the 2 cancels the 2, and I will have at the end lambda equals to L. That is the first basically excited mode, n equals to 3, and so on and so forth. And I was counting the number of NT nodes versus the number of nodes. We found that the number of NT nodes is exactly equal to n, and the number of nodes is just one more than that number, okay? So that is basically, this is for the lab. I know the blue stuff in here is for the lab, not for the lecture. And that is basically in a nutshell what we did last time. There is another part of the story that really needs to be told in this case. And I know we didn't have time really to go through it, but I was going to mention it. And that is the frequency, because the picture is not complete just with the wavelength. We really have to include the frequency. So if we go back to the fundamental mode, and that is when n is equal to 1. And for that, basically the wavelength turned out to be just lambda equals to L over 2. I mean, 2L, I'm sorry, twice the length, okay? In other words, the length is just half the wavelength. So lambda in this case is just 2L. And we already know the dispersion law that links both the frequency and the wavelength, which is lambda f. And for the string, this value is equal to square root of the force divided by the tension, basically divided by the linear mass of the string in this case. So if lambda is 2L, in general, though, we found that basically lambda is 2L over n. So we can plug in this value in here and find the different frequencies for the higher modes, okay? For the other, the overtones, all of the values, basically find it in terms of n. So if I plug in this expression here for the frequency, which is simply equal to I'm going to write it in terms for, this is just for the string. So I'm going to write it for the string because that's basically what we're studying in here. Obviously, the frequency is going to be 1 over lambda, which means n over 2L times the velocity in this case, and the velocity is equal to square root of f, the tension in the string, over the linear mass of the string, okay? So in other words, I can write n as being equal to 1 over 2L times the velocity, if you like, or the n times 1 over 2L times the square root of f over mu. The reason why I want to do it this one is because I really want to isolate n by itself, okay? I want to know what's going on for frequency for different, and this frequency, of course, is for different modes of the excitation of this string. So what I have then is the following scenario. For n equals to 1 for the fundamental frequency, which is f1, it's simply equal to 1 over 2L times the velocity of the wave, which is in this case turned out to be just the tension in the string divided by mu. So this is the fundamental frequency. So if you read any problem and they talk about the fundamental frequency, this is what they mean by it, okay? Fundamental. That means n is equal to 1. So if you're curious about the wavelength in here for this one, of course, it's just twice the length of the string. So lambda in this case would be just 2L. So this is what's going on for the fundamental frequency. Now, for n equals to 2, which is the first overtone, okay, that is, remember, for n equals to 2, now I have 2 NT nodes and 3 nodes, okay? We go back to the picture that we drew last time, basically, when we were analyzing the situation. This situation, when r equals to 2, lambda is exactly equal to L. And in this situation, I have 1 NT node and another NT node and 3 nodes, okay? The 2 where the string is actually fixed, and a third one that develops in the middle that basically will keep this string basically in resonance. This string now is in resonance because of the fact that it's sustained by the incoming wave that is hitting the other side of the string, and when it bounces, it reflects, and that's basically, since it's going usually at high frequency. As a matter of fact, if you watch the video, it's going to basically look as if it's the string somehow changed shape. Instead of being a line, now it has this shape, okay? But this is the first overtone, and the first overtone then in this case, obviously, n is equal to 2, so the 2 cancels the 2, and I will be just left with the frequency f2, which is basically twice the other fundamental frequency. So it's going to be 1 over L square root of f over mu, and so on and so forth. Now, if I want n equals to 3, if I want n equals to 4, and so on and so forth. So basically, you get the picture now. So the frequency now, so this is the first overtone. The second overtone is for n equals to 3, and so on and so forth. So this is basically the picture now is completed. Now, if I want to find the specific value for a frequency, I can either adjust the tension in this case, or I can change the length or do something if I want to excite. Let's say, for example, the frequency is fixed from one end. If the frequency is fixed from one end, then the only thing I can do is adjust the tension. And that is exactly usually what we do, because the person who's playing, for example, with the guitar, then in this case, he's got his own frequency that he's exciting the strings at different rates, depending on what music he wants to play or she wants to play. And in this case, I adjust the tension in different strings to produce different kinds of tones. And those tones basically what makes at the end the notes of the music that is basically known. So again, this is for a string because we use a string in that case. And actually, it's the same thing for the piano too. If you look at the piano, there is actually strings attached to those keys. So depending on which key you're going to strike and how often you're going to strike it, you're going to produce a specific tone again for all of these devices, and to produce those specific notes that you would want to hear. What is it? Do, re, mi, fa. Or, you know, I forgot even what they are called. I have no idea. Don't ask me what music, okay, because I don't know much about it. Anyway, let me We were going to do this experiment, okay? So hopefully when we hit chapter 16, which probably we're going to start today, after we do some examples from this chapter, from chapter 15, then we're going to do an experiment using this very same phenomena, except instead of changing these things, we're going to change the length L, okay? And you can do it at home with a straw. Let me check my straws in here to make sure I have one, okay? Hold on, guys. Let me pause the video quickly. I mean, not pause the video, I mean, stop my camera quickly and grab the, grab my straws. For that, I need scissors too. Okay, here is a straw, okay? You're gonna laugh probably at me when I do it in the class. Apparently some of my students love it so much that I see tears in their eyes. Let me grab scissors and I'll be back, okay? I need to first of all remove this cover from this straw. You need a plastic straw for this one to work, okay? You cannot use a, I know that they are now worried about the environment to the point that they are, okay. So let me prepare this one in the same time. That is basically what I'm doing in here. I'm going to create different tones using this straw, of course, with sound, okay? So let me get the scissors and hopefully get going on it, okay? 1 second. Okay, I got myself some nice scissors. Okay. You come to physics class to be entertained. You don't come to the class in physics to learn. However, there is a risk sometimes when you come to a physics class that you might learn something. So that's something that happens in a physics class too. So I'm just basically making the ads at the end so that I basically produce a nice sound for you guys, okay? I hope you guys have seen the tone changing from different frequencies to a different frequency to a different frequency, and those are the overtones, higher and higher frequency. When I changed the length L, it was long, the tone was high. You guys want to, you can replay this part and see basically how the length in this case, initially the frequency was a high pitch, I mean a low pitch, I should say, like a deep voice, and then it became higher and higher in frequency. So this is, again, it sounds low frequency. I mean, it sounds high frequency, but if I cut the length, in this case, the frequency should go even higher because it's inversely proportional with the length, as you can clearly see from this relationship that I'm describing on the screen here. So again, I don't know if you noticed which change or not, but definitely you noticed it between when it was very long to when it's very short, okay? What happened to my screen now? Okay. So you guys saw the relationship. We do this in class, okay? We have a lot of fun with this thing. Actually, I was thinking one time to quit my physics profession and become a musician by performing on a live audience. And my students never encouraged me to do that. Anyway.
Those were some bad students.
Anyway, you saw the relationship, how the length, as it came down less and less in this case, the pitch changed from a deep voice, basically, which has a low frequency, to a higher and higher frequency. And that is basically the point of this exercise in here, that what was going on in this case, and we're going to see that in chapter 16, are the same standing waves, except that they are actually inside the inside the tube in here. They were sound waves actually, and those sound waves obey this very same relationship. So when I cut the string, when I cut this, not the string actually, in this case the straw, I was making less and less L, which means at the end the frequency went up and up, okay, from low frequency to a higher frequency, okay. So that is this relationship that we're talking about. So that is actually the end of chapter 15. There are some key concepts coming from chapter 16, okay, where we test heavily on them. And those key concepts, namely the Doppler effect and the beats, okay? Actually, the beats, actually, we're going to probably do some of them in chapter 15, at least in terms of exercises, the problems. And then we're going to delve into chapter 16 more in detail about these things, okay? As I promised, we're going to do some problems from this chapter. This is basically the end of chapter 15. Any questions? Okay. And what's my pen to write with? What did it put the pen? Hopefully I didn't take it to another room. It's the pen I write with on this screen in here. For some reason, it's here. Good. Anyway. Okay, not yet, not ready yet. Okay, anyway, so we're gonna do some problems from chapter 15. I'm gonna add a new page in here if you guys don't mind. I'm gonna call it CH15 problems. I promised you guys one problem that I decided against it at this point because it's kind of long, and honestly, probably you're not gonna see that kind, at least in this test. And I'm going to probably give you a solution for it, but basically so that you know how it's handled, because it's a calculus-based problem, and not that it's long. That's all basically for it, and I refrain from it. Instead, I actually chose another problem. So the problems I promised earlier were 66 and 73, and problem 77. 77 I'm going to defer for right now. But I'm going to add problem 67 because they are connected actually. Problem 66 and problem 67, they're connected and they're related to this exact same point that I was talking about the standing waves and things like that, which usually are heavily tested, which is something that you really need to know. Because standing waves occur not just for string, like we just saw them, and the example which I just demonstrated using the straw, the standing waves occur for any kind of basically whatever waves are, and they occur actually in optics a lot, and those are at the heart of the so-called optical fiber optics basically, and telecommunications in general. So this is a phenomenon that is of great importance when we're dealing with these things. So that's why it's important that you guys, so it's not just tuning your musical devices that we're interested in, okay? Although a lot of the examples probably talk about tuning the devices, but it's far more deeper than that in physics and engineering applications, okay? So that's why they are important, okay? And it's a phenomenon of resonance in this case because you have a wave that is continuously created on the other side, basically disturbance that is created, continuously created on the other side, and you adjust your disturbance, your frequency in such a way that the reflected wave in the other one form exactly standing waves. If we do this experiment in the lab, unfortunately, we don't have access to it. You will find that it's not a given that you're going to have standing waves. As a matter of fact, you will have all kinds of disturbance. And if you adjust the weight correctly, because the oscillator on the other side basically have a fixed frequency, you have to really adjust the weights in such a way you're going to produce the fundamental frequency, the first overtone, the second overtone, and all the higher modes basically for the string. And you will see that it needs specific values for the mass, for the other side, for the tension basically in the string to produce those. If you just add, for example, small amount of mass or less amount of mass, you're not going to see that. You're going to see the string going all over the map. So this is a case of resonance. Resonance has tremendous implication everywhere. So it's almost everywhere, and we're going to see that in I know some of you are sitting in physics 4B. You're going to see that also in physics 4B when we do RLC circuits and circuits in general and things like that. Some of you actually sat in my physics 4B in the past, so they know that too. Okay, so problem 66. So it says a guitar is vibrating in its fundamental mode. So you see the key word in here, fundamental mode, that means n is equal to 1. So when I'm, look, 50% of the problem or more is actually understanding the problem. So if you don't understand what the problem is asking or what is it has given, you're not going to be able to basically solve it. So, and those are some of the key words you're going to be looking for. A guitar string, guitar has no meaning. String is a key point in here. That means all of the relationship we've been doing in here all through is vibrating in its fundamental mode. So that means n is equal to 1. That means lambda is equal to 2L. So that's what that means. That means F is equal to 1 over 2L square root of the tension divided by the linear mass of the string. So that's what that word by itself means. Okay, fundamental mode with nodes at each end. So here is basically what they're saying. So we have a node in here and a node in here, and these are the two ends, and this is another end, one of the ends, and this is the other end. And the string looks like this. Basically, it's vibrating in its own fundamental mode. And this is exactly what that is. How many empty nodes it has? It has just one, this one in the middle. And that's it, okay? Because n is equal to 1. Now, the length of the segment of the string that is free to vibrate is 38.6 centimeters. So this distance, basically, they gave you L to be 0.386 meters. So they gave you that information. So we know L now. Okay. The maximum transverse acceleration of a point in the at the middle of the segment is 8.4 times 10 to the power 3 meter per second per second. They tell you this point in the middle, smack in the middle, its maximum acceleration, A, is given by this number, 8,400 meters per second. It's going super fast, basically. That's what it's supposed to do. That's what it's doing. That is exactly what that means, okay? So it's accelerating, but this is the maximum acceleration. So when is the maximum acceleration for the string is going to happen? Basically, if you write the expression, let's say, for example, the wave has this, let's say this point in here, because now this point depends only on time. It doesn't depend on space. But if you care about it in general, everything depends on space and time, okay? So the part that is of interest to us right now, this is in the middle. So it's the temporal behavior that is of importance to us. So if it's a cosine function, cosine of kx minus omega t, we don't care about x is fixed. It's just a number like 12, okay? In the middle, which is exactly 19.3 centimeters from one end or the other, okay? That's basically what x is. It's a fixed number, so we don't care for it. What we care for is this number. So if I take the derivative of y with respect to time, that gives me the velocity, and the velocity should be minus a omega times another minus, that's going to be a positive, sine of kx minus omega t, okay? Again, the x doesn't change. The only thing that is changing in this case is time, okay? And they say the acceleration. So we really have to find the second derivative. The derivative of the derivative with respect to time, I'm going to put another minus in here. So it's going to be a minus a omega squared and another cosine of kx minus omega t. So if you're curious what this number they gave us, this is not the instantaneous acceleration. This is not the acceleration at a given point in time. This is, they said, the maximum. If I read the problem again, the maximum transverse acceleration. So this is the maximum value, which is this number. Okay, that means the amplitude of this oscillation, this distance, times the omega squared is exactly what that number is. Here, by the way, is A. A is this amplitude, okay? times omega squared is 8.4 times 10 to the power 3 meter per second per second. So we know an equation already, A omega squared, that is the maximum. So when you're looking for a maximum, you don't care about sign in this case. You're just looking for the magnitude in this case, how big it is. This number is 8.4 times 10 to the power 3 meter per second squared. Do I know what omega is? They didn't give me. They gave me L. Do I know what the frequency is? They didn't give me that. They gave me L. Do I know what the force, what the tension in the string is? They did not. Did they tell me what type of material so that maybe I can even guess it's mu? No, I don't have anything. So the only thing they gave me is this product, basically, A omega squared, okay? And then they said, and the maximum transverse velocity is 3.8 meter per second. So again, this is how fast this object is moving up and down. It's here at its fastest speed. It stops when it reaches the maximum and comes back, reaches its maximum speed, then it's going to come back down and everything. So if I come back to this expression again, and look at the velocity, this is the velocity. This is the vertical velocity of that point. Up and down, okay, as it's bobbing up and down. That point, its maximum velocity is A omega. So they tell me the maximum velocity, V max, which is this point, this expression, which is just the coefficient of the sign, because the velocity is changing with time, it's going up and down, okay? So in this case, the maximum velocity, they tell me it's 3.8 meter per second. I have two equations with two unknowns. Even if they didn't ask me anything, I can, from these two equations, find both the amplitude of this wave and the omega of this wave. Since I find omega of this wave, then I can find its frequency, because the frequency and omega are related to one another through this relationship. Okay. Since I find omega, I can find F. If I can find F, I already know what L is. So I have some information now about this velocity, basically. Okay. I can find how fast the wave is moving back and forth. This is the velocity of the wave. Has nothing to do with this velocity, by the way. This is the velocity of a point going up and down. There are two velocities in here. The point going up and down, and the wave traveling left to right in this case. This is why it's a transverse wave, because the wave is traveling left to right, but the actual point is going up and down. Okay? So we have omega now. We can find omega theoretically, because from this equation, this one and that one, all I have to do is take the ratio of this number over that number. A cancels A, and omega squared cancels omega. So basically from this expression, omega is equal to the ratio of 8,400 divided by 3.8. And that's going to be the units of a meter cancels a meter, 1/second squared cancel 1/second, and I will be left with 1/second, which is the proper units for an omega, which should be radians per second, and radius is not a unit, it's just a number, okay? So what is the amplitude of this wave? Oh, then it's easy. The amplitude of this wave, actually, we have to find somehow one of these two numbers, or A omega is 3.8. So again, I'm going to find omega from this ratio. A omega squared over A omega, which is exactly omega, is equal to 8,400 divided by 3.8. If I plug in the calculator, and you're supposed to do this part, okay, on your own, okay? 3.8, I'm going to take it roughly to be 4. 4 divided by 8 divided by 4, that is 2. 4 divided by 4, that is going to be 1. So it's roughly 2,100 radians per second. Okay. Obviously, you're supposed to, and this is your task today, basically finish the math, finish the calculations, okay? So you're going to convince yourself of that. So I'm just getting a rough number in here because I don't want to plug in things in the calculator and find these things. So I'm hoping that you guys will have a better answer than this. It's going to be slightly more than 2,100 radians per second because of the fact that I rounded up this number. So if I plug in the correct answer, it's going to be slightly more because I will divide by a less number. Okay? Make sense so far? Yes or no?
Yes.
Okay, so all we want to find is basically now the amplitude. So we know omega, we can use one of the other two relationships, either the first one or the second one, and we're in business. So basically, let's use the second one because it's linear in omega. We don't have to square anything. So A times omega, and omega is 8400 divided by 3.8 is equal to 3.8. And if I divide the units correctly, the amplitude A, the A should be in meters in this case because it's displacement of a string, okay? So it's going to be 3.8 times 3.8 divided by 8400. 3.8 squared divided by 8400. Do I believe this number? Yes. Because the string is 38 centimeters, okay? So this cannot be too big, okay? So 3.8 squared is about 4 squared, which is about 16. 16 divided by 8400, and I'm going to rough it up to be about 8, okay? So I'm just getting estimate numbers, and hopefully you guys will come up with a better answer in here. 16 divided by 8 is about 2, divided by 1,000. So what this is telling me is about 0.002 meters, or 2 millimeters. The string is 38 centimeters, 38.6 centimeters, okay? Half a meter, basically, almost. So these vibrations are about, basically, they go up 2 millimeter up and 2 millimeter down. So they're of a displacement overall of about 4 millimeters up and down, okay? Is this believable? Yes. If I found, for example, a displacement of 17 centimeters or 40 centimeters or something, hey, I have a problem in here. This doesn't make sense. Remember, this whole theory relies on small displacements. So if the string is moving too far up in the guitar, that means it's probably broken. It's not good. It's useless. So this is when I tell you guys to analyze your data to see if it makes sense or not. So this is one of the things, for example, that we look for in here. Obviously, you're going to come up with a better answer than I did because I made so many approximations. I made 3.8 equals to 4, and I made 8.4 equals to 8. So you guys are supposed to plug in the numbers and fix these things in here. But does it make sense? The answer, does it make sense? In this context? That is what you ask yourself. Is it 2 millimeter the amplitude, meaning it's a 4 millimeter, by the way, because it's going to go up 2 millimeter and below 2 millimeter. So it's going to go 4 millimeter up and down, basically, both of them. And the length of the string is 38 centimeters, or 386 times more, or 400 centimeters, basically. So you have 400 centimeters, 400 millimeters, I'm sorry, in length. And this thing is going about 4 millimeter in length, up and down. So this is a ratio of about 1 in 100, okay? So it's still a small approximation. It's 1 in 100 or 0.01, which is acceptable. Yes? Do you see it? Can you at least visualize it? Does it make sense to you guys when you see it? Josh, yeah, okay, very good. So as long as you guys are following and basically doing these things, I'm glad. So this is part 1 of the problem, part A, to find the amplitude. What is the speed for the transverse traveling wave? So this is a transverse wave that is going left and right, okay? And we want to find its velocity. Obviously, we have everything for this expression in here. So this is, by the way, is equal to 1 over 2L times the velocity. We have L, 38.8 something centimeters. We can find the frequency, and we're in business. So the velocity is going to be V, which is lambda times F, and lambda is equal to 2 times L for this problem, times the frequency, and the frequency is omega divided by 2 pi, by the way, because we found omega somewhere in here. Here is omega. So this was omega. All we have to do is divide that number by 2 pi and we're done. So the velocity now, 2L is 2 times 38, or 0.3, I have to use the proper units, meters, 0.386 meters, okay, times omega, which is roughly about 2100. Again, you guys are supposed to come up with better answers, divided by 2 pi, which is roughly 6. Okay, so 2 times 0.3 or 0.8 times 2000 divided by 6 2 times 0.8 is about 1.6 divided by 6 times, and this is 1600 actually divided by 6. So again, I'm just getting an estimate in here, an order of magnitude. I'm not doing the actual calculations, you are. So V in this case is going to be 1600 divided by 6 is about what? 15 divided by 6 is about, what is it, 2.5 maybe? Around 2.5 times 100, so it's about 250 meters per second. Obviously, this number is an estimated, not correct, okay? You guys are, you're going to come up with a better number. But this is the speed of the wave in there, okay? 250 meter per second. This is going left and right, okay? So don't confuse it with the maximum speed of this point going up and down, which turned out to be 3.8 meter per second, okay? So this is this wave going left and right, because it's going at a very high frequency of 2100 radians per second. So that's why it's traveling back and forth between the two ends at this speed. Does this problem make sense? Do you understand the problem first or not?
Yes.
Okay, very good. So now we're going to do problem 67 from the book, okay? Problem 67. By the way, these are typical problems that you might stuff like this one in exams and homework stuff and things like that. So far, so good. So problem 67, which is the replacement for problem 77, basically says, again, a uniform cylindrical steel wire. So the steel wire is uniform and has a length of 55 centimeters. So L is equal to 0.55 meters, okay? So this is steel wire. When they mention the name of a material, usually it's a point to start looking it up on tables, okay? Because if they don't give you some information that you will need for it, then you know what the material is, so you're going to go and find the table in the book and find its properties and so on and so forth, okay? And 1.14 millimeter in diameter. That means the diameter of this thing in here, amen, is, so this distance is 1.14 millimeter, okay? Obviously, this is 55 centimeters, 550 millimeter. It's much, much longer than, so it's a thin one. So the radius in here is even half that value, okay? 0.5 whatever millimeter, so it's a few hundred micrometers, okay? So it's a thin wire, okay? And it's made of steel, so it's important to mention that because we probably are going to look up its properties, okay? It's fixed at both ends, again, so it's like a wire basically fixed from one end to the other end, okay? To what tension must it be adjusted? So we need the tension F. That is to what tension? They are asking for the tension in the string F, okay? Normally the tension in all of your classes up to this point, you use the letter T for tension. But because we have a period that is T, and both of them use capital T, so it might be confused with the period, so that's why we avoid to use the symbol T for the tension, okay? Please make that distinction. Actually, this was probably one of the problems that you guys did in dimensional analysis in the beginning of the semester, where you're given an expression and check its dimensions to a student is confused, is T for tension or T2 for period? And then they use the dimensional analysis to know exactly what this units for this T is. And if it turns out to be Newton or kilogram meter per second, that means that this is actually a force, not a period, which is in seconds. So hopefully you guys pay attention to that. So in here, in this lecture, we're using F for the tension because there is another T that is reserved in this case for the period. And the period, if you guys remember, is related to the frequency via this relationship, okay? That's why we are not using the letter T in this case, okay? And we cannot use a tau because tau is sometimes also confused with the torque in this case. So we don't have torques in this case, okay? At least in this problem. So it's fixed to both ends. To what tension it must be adjusted so that when vibrating in its first overtone, again, these are some of the key words you're going to be looking for. The first overtone means n is equal to 2, actually, if you guys remember, okay? The first overtone means that n is equal to 2. This is the first overtone, okay? Overtone, not the fundamental, but the first one. So that is n equals to 2, okay? So that is the fundamental frequency, and this is the first overtone. The second overtone is actually when n is equal to 3, and so on and so forth, okay? So these are some of the keywords that you're looking for when you're solving problems in this case. So the first overtone means n is equal to 2, which means that lambda is equal to L, okay? Which means that, again, the frequency in this case of the first overtone, which is F2, is just 1 over L, the square root of this tension divided by mu, okay? So that's all of this is just in that one word, the first overtone, or two words in this case, okay? First overtone is all of it hidden in the, has all of these implications in it. So when you're solving problem and you're deciphering basically the problem, this is one of the things that you're supposed to organize as you're solving problems. You're supposed to take a word that is given to you and find what it means, okay? In terms of the things that you know. Since it's a first overtone, that means n equals to 2. That means lambda is actually equal to L. That means I have actually 3 notes and 2 anti-notes. That also is in there in this word. All of this is just means the same thing, okay? So what is it? So the question is still, to what tension must it be adjusted so that when vibrating in its first overtone, it produces the note D sharp of frequency. So the D sharp, apparently in music, is supposed to be of a frequency equals to 311 hertz. So that is what F2 is. So that is what's given to us. So what was given to us is this frequency in here of the first overtone, and we know the length of the string. We are asked to find the force F. We don't know what mu is, but we know that the material has this much diameter and has this much length, and it's steel. So those are the information that we know so far about this material, okay? If I want to find a mu I know if you guys equal to the mass over the length, and the mass of any material is equal to its density times the volume. The volume in this case is just the area pi r squared times the length of the screen. So because this is a cylinder, they tell us also specifically this is a cylinder, and the cylinder, that's also one of the things they tell us in the problem. The base is pi r squared and the length is L. Now the steel has a density, and I think that was part of the lab, of 8,700 kilograms, or 7,800 kilograms, I'm sorry, I put it backward, kilograms per cubic meter. So yes, we can find the mass of this string, okay? Because we know the density is 7,800 kilogram per cubic meter. We know the diameter, so I can find the radius r, which is just half that diameter, times the length, which is given to us. As a matter of fact, mu will be just cancel L with L, and will be just left with, so this is rho times pi times r squared times L divided by L. So the L doesn't matter in this case. The linear mass is going to be rho pi r squared, okay? So we have rho, which is 7,800 kilogram per cubic meter, and we have r that is given to us in millimeter to be 1.14 in diameter. So r is equal to 1.14 divided by 2 times 10 to the negative 3. Don't forget that. That is important because this is in meters now. So we have everything because this unit is in meter. So we have everything. We're in business, it seems like. Okay, so when I square this number, it's going to be meter squared, cancels one of the meter cubed, and it will be left with a kilogram over meter, as this mu is supposed to be. It's supposed to be kilogram per meter, linear mass. So we also can find a mu from the information, and we're given F, the frequency for the D note, and we know the length of the string. So technically we can find this force since they're asking for it, okay? So which is let me finish reading to see if there is anything. Assume that it stretches an insignificant amount. So basically, don't worry about when you, because as it's going up and down, it might stretch a little, so the diameter changes and the linear mass might be distributed a little bit differently. So ignore that, okay? The stretching, the length doesn't change that much, because if it goes up and down, the length changes actually. So it doesn't stay at 55 centimeters. It might go up and down. So we can find the answer to this problem then. From these equations, you can clearly see that F is equal to, the force is equal to F2 squared times L times mu times L squared, I'm sorry, because L squared times, and you just plug in the numbers, okay? So in this case, F2 squared times L squared times mu, and mu is rho times pi times r squared. The reason why I'm interested in the value is because this number is kind of, I need to make sure that it's within a ballpark, okay? So I'm going to estimate things. So this is about 300 squared, or 3 times 2 to the power 2 squared, okay? I'm estimating these numbers now, times the length, and the length is about just 0.5 squared, which is about 1/4, okay? Times rho is about 7,800 or 8,000, times pi, which is about 3, times r squared, and r squared is of the order of 1 divided by 2, which is 1/4 again, times 10 to the negative 6, because this one squared, okay? So that is basically, so 10 to the negative 6, and this 1, 2, 3 0, so I'm going to left with 10 to the negative 3. And I have in here 10 to the power 2 and 2. So that is going to be 10 to the power 4. So all of these powers will be left with just a 10 at the end to the power 1. Okay. And then it's a matter of just finding the rest of the numbers. So what I have in this case is I have 3 times 3, that's 9. I have 7.8, which is 8, divided by 4 times 4, which is 16. And this gives me 2, which is roughly about 400 or 45 newtons, okay? It's not too big, too small, so you guys need to check the numbers for me, okay? The reason why I was scared a little bit when I see things like this one, because I see big numbers and small numbers in a combination. So I want to see if they do any damage to the problem in here. The length is given, all of these things, but it's a length square, by the way. It was half a meter, 50 centimeters. It's 55 centimeters to be more exact. I roughed it up to about half a meter. When you square, it's going to be a quarter. And I plugged in these numbers, and here trying to get an order of magnitude. That's all. It's about 15 newtons, okay? So if you find more or less, please correct that for me, okay? Does this problem make sense to you guys?
Yes, it does.
Okay, very good. As long as you basically decipher the problem and try to understand it, you should be in good shape. So this is problem 67. The next problem is problem 73, okay? Problem 73, basically what it does for you is, again, technically we're supposed to open Excel and plug in the data in an Excel spreadsheet, and hopefully you guys are going to do that because we want to find some plots in here, okay? So this problem in here is, it has different strengths, okay? And with different mu's. So this is string, they call it A. And the mu for this one is 0.026. What are the units? It's in gram per centimeter, okay? Gram per centimeter, okay? It's important to know this is a string. And then its mass in gram is 559 grams, almost half a kilogram, or a little over a pound. Okay. Wow. Does it make sense? That much of a string? So it must be super long string. And D, let me read the problem because I'm not sure. In your physics lab, an oscillator is attached to, no, this is not it. I'm sorry, that's not the mass of the string. It's the mass attached to it, produce the tension. Okay, that's why it's worth reading the problems, okay? So this is how this, the thing looks like. So you have a vibrating in here device in here, the oscillator that is attached to a string, and the string now runs through a pulley, and the pulley has a mass attached to it. This mass produces the tension because mg on this side, okay? This is fixed, okay? Usually you fix it onto the table in here, okay? So this doesn't move. So the string is not in motion. So the tension is going to be exactly mg in this case, okay? And the string throughout the string. This is a massless string, okay? And the mass is big enough so that this point becomes a fixed point in the string. This is oscillating so fast that it's also assumed to be fixed. And this is the length of the string that you're going to be considering L in here, okay? This is the actual experiment that we do in the lab. In the lab, we have a table, and we have actually an oscillator in here that is connected to the power supply that has a specific frequency with which it can produce oscillations. And then the table extends in here, and then this pulley is attached to the table, and then you run the mass on the other side, and you adjust the mass in here because the length is fixed, the frequency is fixed. So you're going to change the mass in here. You change in other words, this force F to hit on different kinds of frequencies in this case. Obviously, the velocity is not going to stay the same. It's going to change from point to point because you're changing the frequency, the force F. So the velocity itself in the wave changes with your changing F. But in this situation, you're going to reach different frequencies depending on the mass in here, depending on the tension in here, okay? So hopefully you understand the problem and how it is structured. In your physics lab, an oscillator is attached to one end of a horizontal string. The other end of the string passes over a frictionless pulley. You suspend a mass m, big M, from the free end of the string, producing an mg in tension, producing tension mg in the string. The oscillator produces transverse waves of frequency f on the string. You don't vary this frequency during this experiment. Usually the device has a fixed frequency, okay? You can't play with it. That's why you can change f, okay? The frequency, that is. You don't vary this for, okay? But you try strings with 3 different linear masses. So you have a string A that has this specific linear mass. So it's one kind, okay? It's made of specific material and specific size and so on and so forth. Specific mass, you weigh it, you take the string, you basically clump it together, and you take it to the scale and you weigh how much mass it has, and then you measure its length, and that's how you find the mu in the lab, okay? That's usually step 1 from your lab, is to find the mu, okay? And then material B has a different linear mass. So material B, apparently, we use it twice in this experiment in here. So a string B actually is 0.0374 grams per centimeter. And it's the same one, 0.0374. And we actually have a third one in here too, material C, that has a linear mass that is equal to 0.0482. This is a little thicker than the first two, okay? So that is material C. Now you change the mass. The mass in here is 559 grams, and in here it's 249 grams, and in here it's 365 grams, and you bring a lower mass in here of 207 grams, you lower the tension. This is 262 grams. Remember, you multiply this number by G, and you multiply it by, or divide by 1,000, because this is in a kilogram, to find the tension in Newton, okay? So that is the weight of that mass that is suspended from the other end of the string. Okay. And then what is this D means in here? because they have this D in here, okay? You also keep a fixed distance between the end of the string where the oscillator and the, so you don't change the position of the pulley and string. Usually they are fixed actually into the table, okay? To produce standing waves on the string, you vary M, then you measure the node-to-node distance for each standing wave pattern and obtain the following data. So basically, you're going to have in here either a fundamental mode or a higher modes, okay? So depending on which one you end up with. In either case, you're measuring this distance between node to node. And this distance between node to node is always half a wavelength. So this distance D that is given to us is just lambda over 2, in other words. And this is in centimeter. So this is lambda over 2. Because the distance between node to node, if you notice in the pattern earlier, it's always half a wavelength. It's always lambda over 2. So this is not given, they did not state that, but this you know from the class, that the distance from node to node is always half wavelength. And if you, let me go back into the lecture in here to see that. When we had a single mode, the first mode, basically the fundamental mode, it's clearly that distance between this node and this node is exactly half wavelength because the wavelength extends a longer way. Now I have a full wavelength. Lambda is equal to exactly L. But between this node and this node, the distance is still half a wavelength. And between this one and that one, it's still half a wavelength. It's always the distance between node and node is always half wavelength. Same thing is true in here. Here, I have lambda is equal to 2/3 of L. So if I extend in here, that is actually the other L, I'm sorry, wavelength. So this is a wavelength and this is a wavelength. But I only have half a wavelength in here for a total of basically the length of the rod being three halves of an L, 3/2 of a wavelength. So this distance is a lambda, and this distance between this node and this node is half a wavelength. This distance and this distance between these two nodes also is a half wavelength, and this distance and this distance is always a half wavelength. So these measurements of D in this problem do not tell me exactly which mode I'm in, but it tells me half a wavelength. Whether I am in the fundamental or the second or the first, it doesn't matter which end it is. The distance between node and node is always half wavelength, okay? So they gave us basically the wavelength, because if I know half wavelength, I know exactly what the wavelength is. I know what lambda is. So this is 48.1 centimeters. This is 31.9 centimeters. This is 32 centimeters. And this is 24.2 centimeters. And finally, this is 23.8 centimeters. So this is lambda over 2. That means lambda itself is twice all of these numbers, okay? Because that's the distance D that is given to me in this problem. And then explain why you obtain only certain values of D. Obviously, because of resonance, if you keep on changing the mass M, you're not going to get standing waves at all. So the only values that you're going to get in here is when there is resonance, and that is specifically for certain values of the force in this case. That is, go back to the lecture, so basically the first question, okay? Question B, graph mu times D squared versus the mass M. Okay, let's see what's going on in here. We're given lambda. Lambda being just 2D in these problems, all of them, because this is the distance between node to node, and it's half a wavelength, therefore lambda is this much, okay? That is one thing. And also, we know that the dispersion law says that V is equal to lambda times F, and V, if you remember from lecture, is square root of F over mu, okay? From this expression here, I can write this one in here as 2D times F, that is exactly what lambda is equal to square root of F over mu, okay? And F is in this case is just mg. So it's square root of big M times G divided by mu, because that's the tension in the string. It's the mass that is weighed on the other side of the body times the gravity in this case. So if I square this relationship, I will find 4d squared F squared is equal to mg over mu. So if I come up with a mu times d squared, the way that they want us to plot it as a function of m, so mu times d squared is going to be equal to m times g divided by 4 times F squared. So this is my dependent variable. Or which, yeah, m is my independent variable, and mu d squared is my dependent variable, okay? So if I plot this, it's going to be a line, okay, of some sort. And this line, the slope of this line is exactly this number. So this is your x, this is your y. So if you plot this, mu times d squared, not mu, not d squared, not d, but the combination mu times d squared, because they tell you specifically in the question, explain, graph mu d squared versus m, okay? Explain why the data plotted this way should fall close to a straight line. So if you plot this, you take mu from here, and you multiply it by this d squared, okay? And if you plot it on an Excel spreadsheet, you're going to find it a line as a function of m, of course, as you vary m, okay? Here is m, 559, 249, 365, and so on and so forth, okay? You're going to find it to be a line, and you know exactly what the slope of this line is. G is 9.8. F is the frequency of that vibrator, of that oscillator. F is the frequency, because it doesn't change, of the oscillator. It's true for all of them, it's the same thing. So it's being controlled by the oscillator. So you cannot change that, and 4 is constant. So this should be that, okay? Does this make sense? Do you guys understand how we arrive into this expression here? Just basically working out this dispersion law, V equals to lambda F, knowing that lambda is twice the distance between node to node, okay? Since that's what's given to us, then times F is going to be equal to square root of the tension, which is mg, divided by the linear mass, in this case mu. So if I work out my algebra, I will find the mu times d squared is just a linear function of m. So if you're changing m, this product of mu times d squared is going to simply be a line, okay? And I know exactly what the slope of this line is. It's g over 4f squared, where g is constant, that's the gravity, and f is actually the frequency of the oscillator. Does this make sense to you guys? The algebra. Maybe? Yes or no? I really need the... This is a lab, really. This is one of the things that we do in a lab in class in physics. Do you guys understand it or not, though? Come on, guys. Yes or no?
Sorry, I was writing down notes.
Yeah, is this so far so good? What do you guys think? Is it... I know I did not do the graph, but I'm counting on... Okay, great. So if it's for the most part, as one of you guys is mentioning, and I understand that, especially since we're not live and doing the actual lab to see this in hand. And actually, this is one of the most exciting labs, I will tell you. I mean, where people start taking pictures of the standing waves and things like that. But this is in a nutshell what's going on in this lab, okay? So this is basically the theory for the lab. If you take this data in here, if you don't believe me, okay? And I know I'm supposed to do this with you guys, but I'm hoping that that's also one of the things you're going to do, because I'm counting on you more and more to do these things on your own. So what I want you to do is take this mu and multiply it by this square d, okay? And if you want to keep the units the same, it doesn't matter. This is in gram per centimeter, and this is centimeter squared. When you square it, of course, it's going to be centimeter squared. The gram centimeter is going to be in the numerator. And then I'm sorry, going to be the y-axis, and this is going to be your x-axis, and plot this thing, it should be a line. If you find the slope of that line, that should be equal to g over 4f squared, okay? Where f is the frequency of this guy, because this was the one that is causing the whole thing to vibrate up and down, okay? So that is basically in a nutshell what this whole lab is, okay? And then use the slope of the best straight line to fit the data to determine the frequency f. Obviously, if I know the slope now, if this is the slope, then I'm in business. The slope will simply be equal to g over 4f squared. And from here, we're going to find f to be just the square root of g over 4 times the slope squared. Times the slope squared times the slope only. Where does the slope squared come from? Okay. So that's the answer for it. So from here, we should be able to pull the slope. I mean, the frequency of that oscillator that caused this whole oscillations. Okay. And on the string, take G to be 9.8. They tell you to take G the correct answer. Don't assume it's 10, okay? So they want to find an accurate value for this thing. So they tell you to take G to be 9.8 meter per second per second. And for D, for a string A, what value of m in grams would be required to produce a standing wave of a node-to-node distance of 24 centimeters? Okay, since we have now the frequency f, okay, since we know what f is now, okay, and lambda we want it to be 24 centimeters, and we want m now to produce that. So for the last part in here, it should be easy because they tell us lambda for that string, okay, for mu equals to 0.026 grams per cubic centimeter. This problem, the cubic centimeter, per centimeter only, it's a linear mass, it's per unit length, not per unit volume. So this is mu, okay? And we want the distance between node to node to be 24 centimeters, meaning lambda to be 48 centimeters, because lambda is 2D, okay? So they want to know the value of the mass m. So you go back in here to the dispersion law that says V is equal to lambda f, and lambda is known. The frequency is known actually too. Lambda is equal to this number, 0.48 meters. The frequency, you calculated it from the previous step. So this is calculated from the slope. So it has to do with the square root of g over, what is it, 4 times the slope of the previous step. And that is equals to the square root of m times g divided by mu, okay? You're given mu, g cancels the g, and you can use the slope or plug in the value of f and find m from this equation, okay? I know I did not do the actual numbers in here since I did not plot this one, but I'm counting on you guys to plot it, get the slope, and get the value of m and put that of your answer. Do these problems make sense to you guys? At least making sense. I know the details are something else, and I really want you to go through the details also. If you have difficulty with them, please communicate that with me. We'll work together on it so that you have full understanding on how to tackle these problems. I need the feedback, guys. Come on, guys. Micah, Harris, Joss, Daniel, I'm sorry, Justin, everybody else. Yes, no, or maybe you need more time to work on this? Okay, at least one person is good. So I'm hoping that you guys will, okay, very good. Okay, so I'm hoping that you guys have spent a little bit of time basically trying to develop this working habits, because believe it or not, the biggest step in solving any problem in physics is understanding what the problem is talking about. Because if you don't know what the problem is talking about, you'll be staring at it, you have no idea how to start it. But if you do the following in any problem, even if the problem I have never basically thought about before, okay, just the first time I look at the problem, the first thing I read, and as I'm reading, try to decipher what those things mean. Every single letter, every single word in there, what do they mean, okay? As far as the lecture, the stuff that I learned before, or the things I know from geometry and things like that. If I start writing while I'm solving the problem, things start to become clearer. Okay? It may not be as clear in the beginning as it was in the beginning the first time around, but if I go through it one more time, it starts to click and connect. Once you have that picture clear in front of you, then it's a matter of just studying the relationship and getting them to get organized and things like that. And that's ultimately how you get the solution. And of course, you have to practice this. That's the purpose of what I'm doing right now, is for you guys to practice on how to tackle these problems so that you approach them with basically courage and basically confidence to be able to address them. Okay, so that's basically what the whole thing is trying to instill in you. Okay, we still have time, and we still have, I know, a little over 10 minutes at least. And so we can introduce the next chapter at least. Good. Okay, so
Sounds good to me.
I'm sorry?
Sounds good to me.
Okay, very good, thank you. So let's share screen now, and let's go into what happened to it. For some reason, it's gone. Show all screens. What happened to my OneNote? Here it is. Okay, so we're going to go into a new page now, and that is chapter 16, actually. And chapter 16 deals with sound. I'm debating, okay, whether or not we should really do the derivation for the sound wave equation, which will turn out to be something like this, okay? A derivative with respect to time of some sort is equal to some positive number, which I can write it square just to emphasize the fact that it's strictly positive, times the derivative with respect to x, okay? Obviously, this is going to be the velocity, okay, of this wave. So what is being taken derivative with? If you like the pressure, we'll put the pressure in here, okay? If you don't like the pressure, we're going to probably put the density in here instead, okay? If you don't like the density, we can find the displacement. Usually it's certain chi in this case, with respect to this variable. So whichever one you like, we can do. Here is the math for it, at least the picture for it, okay? Here is the calm air before sound wave hits the medium, which is the air in this case that I'm taking, okay? It has a given pressure P, which I'm gonna write as P naught. It has a density, which I'm gonna call rho naught, okay? That is its properties. If I come to a point in the air in here, x, and points in space in here, x plus delta x. I have a certain volume in here for a given area A of air. So this is an area A, where I have a certain amount of air in this place, okay? This is undisturbed. Undisturbed. But then the air is not isolated by itself. It's being, it has a pressure on one side from the rest of the air, and it has a pressure from the other side from the rest of the air. So this is what I refer to as P naught. You ask me how much mass of air I have in here? Well, it's just rho times this volume, where rho is rho naught. So this is the calm air. And now a sound wave is produced. So what this sound wave does is it moves this point, it yanks it from its place to another location. It moves this point to another location. So this is how I'm going to visualize it. Now this is disturbed. It's the same volume of air that is being disturbed. So this point now that was in X now has moved to a new location, basically, which is X plus this chi that I'm referring to. This is the displacement in the same direction. This is why this is not a transverse wave. This is actually a longitudinal wave, because the displacement of the mass of air is in the same direction as the wave itself. So the air moved in the X direction and the wave is moving actually in the X direction too. This point that was X plus delta X now moves to a new location, which is basically expressed by this displacement of delta chi, okay? So chi in this case, or big X, sometimes I write it as capital X versus lowercase x, just to make the distinction between the two. If you are not used to the chi letter, which is the Greek letter for the displacement in this case, this is now what happened to that mass of air after the wave has gone through it. Obviously, the pressure looks, the density looks less now. So the density has dropped because of this dropped, okay, because of this disturbance. And now I basically have this behavior of this wave in here. So here is the deal. If I find how the pressure has changed from this point to this point, okay, I will attribute that change in the pressure due to our friend sound. So the change in pressure is due to sound. If I want to find how much the density has dropped, this is the density, by the way, because the pressure from one side, it's still P, but this P now is measured at a different point in space because this point X has shifted. So this P now has shifted to an X plus chi. And again, it may be time dependent too, because this whole behavior is time dependent. So this chi actually depends on time, because this wave comes in and then moves back the air. So these molecules of the air will stay in their place. So the air will go back and forth, but the wave itself is the one that is traveling. Yes, the molecules of the air, they move back and forth. They have their thermal agitations. They're moving everywhere in here. And we will know about that in chapter 17 and chapter 18. But the point being in here is that the bulk of the air, basically, as far as sound is concerned, is basically being yanked back and forth. And the disturbance will travel until it reaches the receiver, for example, the ear. So by the time it reaches the ear, this motion of the air back and forth will reach the ear and basically make the drum move back and forth. And that is how you interpret sound. So that's basically how sound is traveled in this case. And it's expressed also in terms of this pressure drop. And this is the change in the density, in this case, is due to sound. Change in density is due to sound, okay? To sound. Okay, the math is kind of tedious, honestly, and I really don't want to go through it. I recommend Feynman lectures. It's the best way of doing this. The book tries at it, honestly, but doesn't do a good job at it, so it's not really good. Furthermore, in order to really understand the speed of sound will turn out to be, for this case in here, which I'm going to give you the expression for it, V for a fluid is equal to the bulk modulus divided by the density of that fluid. So for the air, it's the bulk modulus. Did you guys do that? You did that in physics 4A, didn't you, when you did elasticity?
I'll be honest, I don't remember.
When you did elasticity, how basically the tensile basically properties of materials when they are stretched and change in length, and you guys probably, and Young modulus. As a matter of fact, in the case of solids, it's Young modulus divided by the same thing, the density for the material. So this is for a solid, actually, for example, for an iron, and this is Young modulus. This stuff is in physics 4A. And this is the density in both cases, just the density of the medium. If we're dealing with steel, that's still 7,800 kilograms per cubic meter. That is the same value in there, but I have to look at the table in there to find what the Young modulus is. So again, if you're not familiar with those things, please, you really don't need them. You just consult the table and find what B is for the air and what Y is for steel, if you're using steel or copper or whatever material you're using, trying to find sound propagation in it, okay? Again, we're not going to do the derivation now because, like I said, it's really long and tedious and it's really going to yield these expressions. However, there is an important relationship on how the velocity of sound depends on T, on the temperature. And for that, we have to use actually something that is coming in chapter 17 and chapter 18 and chapter 19 in big time. And that is the so-called inert gas laws. For those who did chemistry, you know about PV equal to nRT. You guys know this from chemistry classes? Did anyone of you take chemistry at all? The ideal gas law. This is the ideal gas law. Okay. And there is a Boltzmann interpretation of this law, which says that PV equal to NKBT, which we're going to do in this class. All of this, we're going to do them in the near future, actually, not too long from now. Actually, they're going to be part of exam 1, okay? So we're going to take this expression, actually, and find an expression for how the velocity of sound depends on temperature. And for that, we're going to do some processes because Newton himself, when he tried to explain this thing, he assumed that somehow when sound travels from point to point in space, there is not enough time for the temperature to change. So he assumed the sound propagates with constant temperature, but as it turns out to be not correct. The correct treatment is that there is no time for heat to be exchanged, not temperature. And those are two key different concepts. And for that, we use a different process for it, and we have a better explanation for this, how the temperature depends on the pressure, first of all, how the pressure is related to the density, and how it depends on temperature too. The bottom line is the velocity of sound will turn out to be some fixed velocity times 1 plus temperature in Kelvin divided by some constants in here, okay? Divided by some T constant, which is the room temperature. So the change in temperature, by the way, okay? And this is room temperature. Okay, we're going to come up with a better explanation for this thing in here down the road. So I'm not really going to emphasize on these things in here. What we are going to emphasize on in this chapter, we have 2 minutes in here, is the intensity of sound. And the intensity of sound as being produced from a sound source is going to be the power of the sound. And the power, we saw how the expression looks like in previously, which is 1/2 times the amplitude squared times omega squared times the velocity of the wave, okay? So this power, which is expressed in watts, and the intensity is defined as being equal to the power over the area with which it's going to be spreading, so 4 pi r squared. So the intensity is going to be watt per meter squared. We don't use this for sound specifically. We use another unit. Actually, we use the intensity in decibels. So again, this is just preview to what we're going to see on Tuesday, decibels. So the intensity I in decibels, this is the units dB, is by definition some log 10. Is it 10 or 20? I don't remember. I think it's 10. Depending on where it's 10, it's 10. Okay, depending on how you choose I naught, and I will tell you what I naught is. Log in the base of 10. I know you're used to the natural log a lot, but this definition uses the base of 10 of the power in this case, or the intensity in this case, the absolute intensity as defined in here. So this intensity is in decibels. So probably we use beta for it. I'm sorry, just remember the unit for it. So we use beta on it. So this is still intensity in decibels. Okay. Whereas this intensity is still watts per square meter divided by some I naught. And I naught by definition is equal to 10 to the negative 12 watts per meter squared. This is the threshold of hearing. If a sound has less intensity than this one, you cannot hear it. So this is barely the sound that you can hear. All the way to an that's why we use a logarithmic scale, because the intensity of pain, the threshold of pain, I of pain, is about 10 to the power, what is it? 12. It's about basically 12 decibels. Beta is equal to 120 decibels. Okay. So we're going to come up with this expression and basically plug it in. It's about 1. I is 1 watt per meter squared. Okay, time is over anyway, so we can't really continue this discussion. So this is just an introduction to sound, if you like, okay? So more on this chapter on Tuesday, and as promised, we're gonna have more problems. The more interesting stuff from that chapter are beats and Doppler effect, though, okay? So those are the things that are gonna be heavily tested and examined and things like that in terms of this class. I will see you guys Tuesday, and please keep questions coming. And watch the video in here again. Mainly today was about the problems that we did today from this chapter 15. And you're supposed to finish the algebra and make sure you go through each and every one of those problems and do them. Okay? You guys don't have any questions? I'm going to stop sharing. Justin, were you saying something?
No, I'm just gonna say I'm all good here.
Okay, very good. So let me stop sharing. Stop recording. I'm sorry.